Welcome to another Mathcast. In this episode we're going to be taking a look at polar curves and how to find the arc length of a polar curve. We're starting off today with a cardioid, which is sort of a deformed circle on one side, and it's given to us by the equation 1 plus cosine theta. Now let's recall for arc length involving parametric curves that the arc length integral is the integral from theta 1 to theta 2, where this is our starting angle and our finishing angle, and it's the square root of r squared plus dr d theta, quantity squared d theta. So you're integrating with respect to the angle, and the two key components are the polar curve itself, written in terms of r, and the derivative of the curve with respect to theta. So we're already given r. Let's go ahead and find dr d theta. So dr d theta here is the derivative of cosine theta with respect to theta is minus sine theta. Alright, keeping that in mind, let's go ahead and go over to the curve. We need to determine theta 1 and theta 2. Well, we know that theta 1 is 0 because if you plug 0 into our value of r here, you get r at 0 is 1 plus cosine of 0, which we know is equal to 2. So cosine of 0 is 1, you get 1 plus 1, or 2. And so we are exactly where we would expect to be. At an angle of 0, we're out at radius 2. And we've seen this curve enough over the course of the semester to know that the curve itself, as it's traced out from 0 to pi, you get the top half, and then pi to 2 pi traces out the bottom half. Alright, keeping that in mind, we're going to start with theta 2 equal to 2 pi then. And there's a lot of different ways you could handle this. My preference would be to probably just multiply the length by 2 since we're using the symmetry here, and to say that the arc length is twice the integral from 0 to pi of the square root of r squared plus dr d theta squared d theta. So if we update this integral, this would be the integral from 0 to pi of r squared is 1 plus cosine of theta, and the whole thing is squared. That's a quantity squared, plus minus sine theta, quantity squared, d theta. Well, if we do a little bit of work here, we can mess around with some things underneath the radical. If we factor everything out, this will give us a 1 plus 2 cosine theta plus cosine squared, and we're sort of lucky here. The minus sine theta becomes a sine squared theta, and you should immediately recognize what you would want to try to do next, and that's to take this quantity and set it equal to 1. If we do that, we get the following. You've got a 1 here and you're going to get a 1 there, so it'll be 2 plus 2 cosine theta d theta. And I'm going to go ahead and factor out the 2. If I do, that factors out as a root 2. And I'm left with 1 plus cosine theta. Now, this integral is down to a really good simplified form, and I am tempted just to leave it here because that's a really difficult integral to calculate. If you want to do this by hand, let me give you a couple of hints. You should do 2 substitutions here. The first substitution that you should try is you should try to let u be 1 plus cosine theta, which will make the du minus sine theta. What you're going to run into is this minus sine theta can't be accounted for, but we can write that term in terms of u because we can look at the following triangle. Remember when we did this back when we were doing our trig substitutions? This comes into play here. If this is the angle theta, then setting u as 1 plus cosine theta is the same thing as writing u minus 1 equals cosine theta. And so that would put a u minus 1 on the adjacent and a 1 here. And then if you solve for this other side, you get something that's sort of unpleasant here, but we can still work with it. And it's the square root of u to 2 minus u. That means that minus sine theta can be represented as minus the square root of u 2 minus u. If you make these substitutions into this problem, you'll come up with an integral that we can solve pretty easily. It just takes a little bit of work. And you should get an answer, surprisingly enough, of 8. And so I would encourage you to go ahead and work out the integral to see if you can't match this result. Oftentimes when you're doing these polar curves and you're looking at the arc length, we've already seen in class how it winds up being a trigonometric integral at some point. Either we have to use some of our rules from earlier in the semester, or we have to use a trig substitution. And so just keep in mind a couple of those things we learned early in the semester. You can't really forget about them at this point. Although I am very happy if you're able to get to the boxed answer I have here where I've set up the integral. That's going to be the main focus of the exam coming up, is the ability to set up the integral. All right, thank you for watching.